Part B. When 250 milligrams of sodium was added to 500 centimetres cubed of water at 25 degrees C, a gas was produced. So let's break this question down. So let's call that A, let's call that B. And so give an equation for the reaction that occurs and then calculate the volume in centimetres cubed. So this is something that once you've done the calculation you might forget. There is actually a reminder down here, so that's good. 250 milligrams, let's convert that straight away. So that is 0.25 grams. Okay, so let's start with the equation. So we've got sodium reacting with water, so metal and water is going to make the metal hydroxide, so sodium hydroxide, and then metal plus water makes the metal hydroxide and hydrogen, which gives us that. We then just need to balance it with a half in front of here. State symbols will be good, but on the mark scheme not necessary. It's always good to put state symbols in because if they're not required, they won't be marked even if you get them wrong. If they are required, obviously you're in the habit of writing state symbols. So as the sodium hydroxide forms, it will dissolve in the water that we've got here, which is why the state symbol here is aqueous. Okay, so that's the equation. Let's do part B. So part B, calculate the volume of the gas. So this is a PV equals nRT calculation. So PV equals nRT. First thing I'm going to do is rearrange it. So V equals nRT over P. Okay, so there's usually 1 mark for rearranging it. So next thing I'm going to do is I'm going to put my values in. So V equals, so number of moles I haven't got, so I need to work out the number of moles. Let me work that out over here. So I need the number of moles of hydrogen, and I can only do that by looking at the moles of sodium because I have a mass of sodium. So the number of moles of sodium is equal to 0.25 divided by 23 off the periodic table. That equals 0.0109. And in the equation here, for every one of these, I make half of those, so that's a 1. So what I need to do here is divide by 2 to get the number of moles of hydrogen. So number of moles of hydrogen is 0.0109 divided by 2, which gives me 5.4. There's a range in here, so let me get my calculator and work that out properly. So 0.25 divided by 23, that gives me 0.109, divided by 2 equals, so on my calculator it is 5.43, so 5.43 times 10 to the minus 3. So I've got n. So let me just move this over a little bit, so I've got plenty of room for that. So V equals 5.43 times 10 to the minus 3 times R, given in the question, times the temperature. The temperature here is in degrees C, so I need to add 273 to that, which is going to give me 298, and then the pressure is in kilopascals. So that needs to be in pascals, that's going to be times 10 to the 3. So temperature then, 298, divided by the pressure, 101, times 10 to the 3. So that gives me a volume, if I plug that into my calculator, so that gives me a volume of 1.33 times 10 to the minus 4. Now that will be meters cubed, and the question, look, is asking for it in centimeters cubed. So centimeters cubed, decimeters cubed, that's a factor of 1,000. Decimeters cubed to meters cubed, that's a factor of 1,000 as well. There's more centimeters cubed than meters cubed. So what I need to do here is times it by 1,000,000. So volume in centimeters cubed is going to be 133. So down here that will be 133. So there's a lot going on here. So let's just have a look at where the marks are for this question. So obviously there's a mark for the correct balanced chemical equation. There's one for working out the number of moles of sodium. There's one for working out the number of moles of hydrogen. There's one for converting the temperature and pressure, and those are in here, so I'll put that there. And there's one for rearranging the equation, which you can get from this or you can get that from there. Okay, so either or there. Obviously there's then one for the correct answer. So that is this one here. So 1, 2, 3, 4, 5, 6. Okay. So let's move on. So B, calculate the concentration in moles per decimeters cubed of the sodium ions produced in the reaction in part B. Okay, so the sodium ions are coming from the dissolved sodium hydroxide. So what happens with these ions is they dissociate in solution to give aqueous sodium ions and aqueous hydroxide ions. So if I know how many moles I have here, that's how many moles I have there, which then allows me to work out the concentration. And of course, in the equation at the top, we've got the number of moles of sodium here. So if I know the number of moles of sodium here, it's a 1-to-1 ratio now. So I know the number of moles of sodium hydroxide. And if I know the number of moles of my sodium hydroxide, that's equal to the number of moles of my sodium. So this is a fairly straightforward one. So concentration is number of moles divided by the volume. Number of moles, as calculated in the previous part, is 0.0109 divided by the volume. Now the volume won't have changed, so that's still 500 centimetres cubed. And remember that's got to be converted to decimeters cubed, so times 10 to the minus 3. And that gives you a concentration of 0.0217 moles per decimeter cubed, so there'll be 1 mark for that. Part D, sodium reacts with ammonia to form the compound NaNH2 that contains the NH2- ion. Draw the shape, include any lone pairs of electrons that influence the shape, and then predict the bond angle and justify your prediction. So quite an open-ended question, which with A, B, C and D I've managed to kind of create a structured question here. So let's work out how many pairs of electrons are around the central atom. The central atom is nitrogen. So nitrogen is in group 5, which means it has 5 electrons in its outer shell. The minus charge means it's got an extra electron, and each hydrogen brings a 1 electron each to a covalent bond. So that is going to give me 5, 6, 7, 8 electrons. Now remember they're in pairs, so that means I'm going to have 4 pairs of electrons. Okay, so the shape I'm starting with, if this isn't the answer. If I put nitrogen in the middle, it's starting with that, isn't it? Because 4 pairs is this. But on my molecule here, I've got 2 covalent bonds. Now, if I've got 4 pairs, that means I have 2 lone pairs of electrons in here. So what I'm going to do is I'm going to rub 2 of these out and make them lone pairs. And just because it's easier to do, I'm going to do those 2. So put a lone pair on here and a lone pair on there. Put my hydrogens on the end. Now it's negatively charged, so strictly speaking I should put brackets around it. But the mark scheme does state, not to worry about the brackets. So draw the shape. There's the shape. Include lone pairs that influence the shape. I've done that as well. So I've done A and B. Okay. Part C, predict the bond angle. So tetrahedral has a bond angle of 109.5, and we take 2.5 degrees off per lone pair, and I've got two of them. So that's going to leave me with a bond angle of 104.5 degrees. So there's the bond angle. And then I need to justify the prediction. So the bond angle is 104.5. The justification is that pairs of electrons repel around the central atom as far as possible. Now, if there were all bonding pairs, that would be enough, but I've got lone pairs in here, so I need to state the effect of the lone pairs. So, lone pair to lone pair repulsion is greater than lone pair to bonding pair repulsion, which is greater than bonding pair to bonding pair repulsion. Okay, so in terms of the marks here, so there is 1 mark for the correctly drawn shape with the lone pairs on. There's 1 mark for the correct bond angle. There's 1 mark for saying that pairs of electrons repel as far as possible, and there's 1 mark for basically stating that lone pairs repel more than bonding pairs.